March 21, 1986, Tyler, Texas. A man lies on a treatment table. The machine turns on. He feels an intense electric shock, like being struck by lightning through his spine. He screams. He runs out of the room. The operator checks the screen. It says, "No dose delivered." The machine is lying. That man received 125 times the prescribed radiation dose, in a beam the size of a dime. He died 5 months later, and the manufacturer spent the next 2 years insisting this was impossible. This is the story of Therac-25, the most lethal software bug in history, and the lesson every developer needs to hear before shipping another line of code. To understand how software killed people, you need to understand the machine. A radiation therapy machine treats cancer by firing precisely calibrated beams at tumors. 2 modes. Electron mode. Low energy treats surface tumors. X-ray mode. High energy reaches deep. Here's the critical part. In X-ray mode, the electron beam hits a tungsten target, which converts it into X-rays. A beam flattener spreads those X-rays evenly across the treatment area. Now imagine the machine fires the full-power X-ray beam, but the tungsten target and flattener aren't in place. No conversion, no spreading. The patient gets a concentrated blast of raw electron energy, hundreds of times the intended dose. That's exactly what happened. But here's the twist that makes this story terrifying. The previous model, the Therac-20, had hardware interlocks, physical safety mechanisms that physically blocked the beam if the turntable wasn't in the correct position, metal stops that didn't care what the software said. The Therac-25 removed them, trusted the software instead, and the software had bugs. The entire software controlling this machine, beam selection, turntable positioning, dose calibration, and safety checks, was written by a single programmer, one person, in PDP-11 assembly language, no high-level language, minimal documentation. The code evolved from the Therac-6 in 1972 through the Therac-20 in 1976 to the Therac-25 in 1982. A decade of accumulated, barely tested legacy code. No peer review, no independent testing, no formal safety analysis. And when the accident started, when lawyers tried to find this programmer, they couldn't. The programmer had left AECL in 1986. Their name was never identified. Their qualifications were never determined. The person who wrote the code that killed people simply vanished. Think about that. The code was still running. The patients were still dying. And the person who understood the code was gone. But we'll come back to that. Because first, the machine started hurting people. June 3, 1985, Kennestone Regional Oncology Center, Marietta, Georgia. Katie Yarborough, 61 years old, being treated for breast cancer. The machine fires. She feels a tremendous force of heat, a red-hot sensation in her chest and arm. She looks up and says, "You burned me." The operator checks the screen. Everything looks normal. Katie received between 15,000 and 20,000 rads. She was supposed to get 200. That's 80 to 100 times the prescribed dose. Her breast had to be surgically removed. She lost the use of her arm and shoulder permanently. She lived in constant pain for the rest of her life. And the manufacturer, AECL, was notified. Their response: overdose is impossible. They sent a letter, 2 pages, explaining in detail why this could never happen. Not machine failure, not operator error. Impossible. So the machine kept running, and the accidents kept coming. If you're a developer watching this, subscribe. Because what happens next is the part they should have taught you in school. 9 months later, March 1986. East Texas Cancer Center, Tyler, Texas. A patient named Ray Cox lies on the table, prescribed 180 rads for a tumor on his back. The operator sets up the treatment, electron mode, types the parameters, then notices a mistake. It should be X-ray mode. She quickly edits the field and presses the set button. The machine fires. Ray feels an intense electric shock. He screams. He runs out of the room. He later told a friend, "Captain, I got fried." The display shows malfunction 54. The operator has seen this message hundreds of times. It appears about 40 times a day across Therac-25 machines. Operators have learned to press P for proceed. The machine had trained its operators to ignore warnings, but this time was different. This time, Ray Cox received an estimated 16,500 to 25,000 rads in a dime-sized area on his spine. The radiation slowly paralyzed his left arm, then both legs, then his left vocal cord, then his diaphragm. 5 months later, Ray Cox was dead. Cause of death, radiation overdose. Hospital physicist Fritz Hager didn't accept AECL's impossible. He spent weeks trying to reproduce the exact sequence of keystrokes. AECL told him he was wrong, but he found it. The exact keystroke timing, the exact edit sequence, the proof. And while he was still trying to convince AECL, 3 weeks after Ray Cox's overdose, it happened again. Same machine, same hospital. Another patient. He saw a bright light, heard eggs frying, said it felt like his face was on fire. He died 3 weeks later. Massive radiation overdose to his right temporal lobe and brainstem. Same machine. AECL still hadn't recalled it. So what was the bug? A race condition. The kind of bug every developer has encountered, but never imagined could kill someone. Here's how it worked. A variable called class 3 was stored in 1 byte of memory. Every time a certain routine ran, it incremented by 1. What 1 byte means 256 values. On the 256th time, it rolled over from 255 to 0. If the operator edited the beam parameters, switching from X-ray to electron mode, at the exact moment class 3 rolled over to 0, the software would set the beam to full X-ray power, 25 million electron volts, but it wouldn't move the turntable. No tungsten target, no beam flattener, raw concentrated energy directly into the patient. The timing window was approximately 1 in 256, rare enough to slip through testing, common enough to kill. And here's the cruelest irony. The Therac-20 had the exact same bug, the exact same race condition, and the exact same reused code, but the hardware interlocks caught it, metal stops that didn't care about byte overflow. For 10 years, hardware had been silently saving patients from a lethal software bug. Nobody knew. Nobody checked. Then, AECL removed the interlocks, trusted the software, and people died. February 6, 1987. The FDA issues a Class 1 recall, the most serious category. Reasonable probability that use will cause death or serious health consequences. All 11 Therac-25 machines across the U.S. and Canada. Shut down. 6 patients had been overdosed, 3 dead, 3 permanently injured. AECL was forced to do what they should have done years earlier. Reinstall hardware interlocks, redesign the software, fix the error messages, make the machine tell the truth. It took AECL 6 more months to get FDA approval for their corrective action plan. In 1990, Congress passed the Safe Medical Devices Act, requiring hospitals to report device incidents. Because before Therac-25 they weren't required to. Nancy Leveson, computer science professor, spent years investigating the Therac-25 accidents. Her paper with Clark Turner became the most important document in software safety history. She wrote, "A naive assumption is often made that reusing software increases safety because the software has been exercised extensively. Reuse of software modules does not guarantee safe behavior." The Therac-25 case is now taught in every computer science ethics course on the planet. Not as history, as a warning, because the pattern is happening again. Right now, AI models are making medical diagnoses. Autonomous vehicles are making life or death decisions at highway speed. Automated systems control power grids, air traffic, financial markets, and the same assumption keeps being made. The software is good enough. We don't need hardware failsafes. The algorithm has been tested extensively. Has it? How do you test for the 1 in 256 edge case? The race condition that only triggers when someone types too fast? The byte overflow that's been hiding for a decade in reused code? Here's what stays with me about Therac-25. Katie Yarborough said, "You burned me." The operator saw nothing wrong on the screen. Ray Cox screamed and ran. The screen said no dose was delivered. The machine lied, and people trusted the machine. Every time you ship code, you're asking someone to trust you. Maybe it's just an app that freezes. Maybe it's a payment that fails. But maybe, somewhere down the line, it's a machine that controls something that matters. Have you reviewed your dead code lately? Do you know what's still running from 10 years ago? Have you checked what happens on the 256th cycle? The bug is always patient. It waits. That patience reminds me of another story. In 2003, a team of engineers at Knight Capital deployed an update to their trading servers, but they forgot one. One server out of 8 still ran code from the year 2000. When the markets opened, that forgotten server started buying high and selling low, at the speed of light. 45 minutes later, Knight Capital had lost $440 million, and nobody could figure out which server was doing it. That story, next time. Title suggestions. 5 options. 1. The race condition that killed. Therac-25 story. 2 but 200 rads. Prescribed. 25,000 delivered. The code that killed. 3. You burned me. When a software bug kills patience. 4. 1. Programmer. 0 code reviews. 3 deaths. Therac-25,000. The machine lied. How a race condition killed 3 people.